Okay. How you guys doing?
Good. Ready for Easter.
Ready for Easter? Do a lot of people kind of go on a bit of a holiday, like take little trips and things,
I'm gonna have
or
a holiday tonight.
just just family
I'm
time?
gonna have a holiday with my friends tonight.
Oh, no family for you.
My grandparents just got out of the hospital. My cousins all have it, or just had it. My aunt has it. My dad has it. So like, we're not gonna be able to do it.
Right.
Oh.
Okay. So we're gonna get going with chemistry now. Now that we've covered Sudoku, celebrity science culture or something, and flu, and did I overhear some bloodletting or blood drawing stuff? Not letting that. Okay. Yeah, the nurses always love when I show up to get my blood drawn because it's just ready.
My thing's really visible, but it's not like that.
How do you do that?
It just happens. And then at one point, so TMI medical, I had like this little subcutaneous cyst in my armpit one time. So now this arm just always looks a little slightly more swollen if I have anything going on in my lymph nodes. It's like it just pressed up against the lymph thing and just weird. Anyway, the one day I wear my sleeves curled up. Okay, so back to solubility and things like that. So last time we went over the exams, and then we went through a quick example talking again about this ion activity product. I wanted to give you a little more practical, okay, what do we do with it? So we talked about this stannous fluoride SNF2, did a little practice problem there. And there's also a couple other really simple things we can do with this ion activity product, basically just comparing it to the solubility, right? And if you think about it, that's what I've been saying. Is it higher? Is it lower? Well, we can formalize that a tiny bit and say, okay, let's take that ion activity product and divide it by the solubility product, the equilibrium constant, right? So we could call this a saturation index to say how saturated are we? Is this solution, let's say, of sugar or of sodium chloride or something, right? And the way we can write that is simply that ion activity product over the solubility product. So normally we would consider, a random solubility product for, let's say, some solid AB that dissociates to A plus and B minus, something like that. The solubility product would then be, well, really the activity. So we'll be proper for a moment, of A times the activity of B divided by 1, because the activity of a solid becomes 1. Right, this goes to 1. So it really just becomes the product of those two products of the reaction, right? So we've talked about this a lot, and usually we say activity, we'll assume it's 1 and carry on. So that would be the solubility product. Well, we also said that the ion activity product is basically the exact same thing, except it's, instead of defining it as what the conditions are at equilibrium, the ion activity product is simply what the conditions presently are, right? So we are figuring out in a given situation, maybe we heated something up real hot, added a whole bunch of salt, supersaturated it, cooled it down real quick, and suddenly in that moment, our ion activity product might be out of equilibrium, right? We might be supersaturated. Or maybe we just didn't add enough to saturate it in the first place, so we just have some, but not nearly enough. So this would then be essentially the same thing, A times B, but in the present moment. So that means when we look at this equation, the ion activity product over that equilibrium, If it's less than 1, we know we have undersaturated. If it's greater than 1, then we have essentially more concentration with respect to in solution compared to what we would have if we let it reach equilibrium. Okay, so that's if this value for this Si is over 1, we know it's supersaturated. Okay, so we could say it's twice as saturated if we've got it to 2. Now, that's pretty handy, but there's one other thing we can do to it which helps us map it out in terms of on a kind of a more of a molecular scale, and that is to take that exact same equation and call it a saturation ratio by raising it to the 1 over V power, and V being the number of ions in it. So maybe we have some solid that has 3 different ions that forms it. For example, we talked about this stannous fluoride stuff. There's actually tin, SN, and 2 F minuses, right? Or we'll see in a few minutes, I think it's struvite, we have several different ions that come together to form the solid. So you can have solids that have multiple different ions in it, and this is a way to normalize it for that. So very simple. I'm going to go ahead and give you these on the exam. I'm not sure, probably, I guess announcement here, I will be working to get you a homework posted probably by next class, MATLAB and like a typical homework. So be looking out for that, but after Easter, and that'll kind of bring us to a close for the semester. So I don't think we need to use these a ton, but we can do a little example, see how we might want to use them. So take a minute and look at this problem. So I'll read it and give you a couple minutes to think about it, and we'll just, it's a very simple calculation to make and then thinking about it from there. So we have a water that has a calcium activity of 10 to the minus 3.5 and a sulfate activity of 10 to the minus 1.5. By how much is it undersaturated or supersaturated with respect to gypsum? And I went ahead and grabbed the gypsum solubility product here. Then also, by how much would we have to concentrate it or dilute it in order to achieve that equilibrium? So give that a couple minutes to think about it. Do you?
Do you use the saturation index to find the ratio and then the fraction and then the ratio to find how much IAP should be going into it to like become a ratio of 1?
Say that again.
So like you use SI, like IAP over KSP to find just the ratio, like how far it is from equilibrium, and then
Yeah.
you use the SR equation to find like the ratio of which like they're related to each other.
Yeah. So the question is, why the difference here in SI versus SR, basically, right? The SR, I'm not going to bother working to derive this. I didn't want to spend too much time on it, but it lets us have a much more straightforward way of understanding how much water we need to add. Because anytime if we have one molecule that is between a solid and a dissolved state somehow, maybe, I don't know, water freezing or something, then any dilution that you do to that one molecule, you add some volume and it's immediately, you have the right effect. But if you have two molecules, suddenly, anytime you add one volume of water, you're adding that to both molecules, and that's changing both activities. So you need a square root type of an equation. And so that's where this 1 over V is coming from. Because if you dilute it or concentrate it, you are changing multiple volumes with every change in volume that you make. So in order to account for that, we need to do this 1 over V thing. So everybody feel like they got at least a little bit of it? And by the way, do you want me to make these larger in general? Would that be helpful? Do you want me to try to make these larger? Okay. Okay. So the IAP then, like we said, this should be the activity, two activities times each other. And we were given both activities, 10 to the minus 3.5, 10 to the minus 1.5. So really we can just add those exponents, so it should become 10 to the minus 5, if I'm not mistaken on that. Then we could say our saturation index would be 10 to the minus 5 divided by 10 to the minus 4.6. And just looking on that, that should become, what, 10 to the minus 0.4, I think, right? So what is that value?
1.5119 times 10 to the minus 5.
I don't think so.
Wait, oh, I'm tripping. 0.39.
There we go. That sounds better. I'll believe that one. Okay. Okay. Does that make sense so far? Okay, so we get a value there, and then to do the S.
Does that indicate that it's undersaturated?
Yes. So yeah, I should address that first. So that means this is undersaturated for sure. And it feels like we should say it's like 39% of the way to saturation, right? That's kind of like the feeling of it. But like I said a minute ago, as soon as we start concentrating this, we're not just concentrating one molecule at a time. It's going to concentrate multiple at a time. So that's where we get the saturation ratio. And we'll go ahead and calculate that. That should be 0.39, the square root of it, really, raised to the 1/2, right? So when we get that, that should be, is that just 0.13? So this, no, that's, I was thinking 13 times 3, not, sorry. Anybody have that number? Square root of 0.39? 0.62. Okay, thank you. So that would essentially indicate that we are, and I have somebody online, so thank you for participating here, but we'll get, they're saying the answer is 1.58, but we're going to get there in a second. So the 0.62 is our saturation ratio. That means we are, now that's probably a better way to say we are 62% of the way to saturation. So in order to figure out, well, how much concentration do we have to do in order to get there, what we can do is simply do 1 over this saturation ratio. So 1 over 0.62. Somebody have that for me? 1.61. Okay. So yeah, quite close to what was being said here. So depending on how we carry the decimals or whatever, you know, maybe it's 1.58 or maybe 1.16 is closer. But that's the process, right? So we would say we can concentrate it by a factor of 1.61, and then we will reach saturation. Okay? So just wanted to show that neat little thing. I think I made a typo when I was writing that out. So. Okay. Okay, so that's another thing we can use. It's a nice little tool, not anything super fancy. Most of what I wanted to do today is talk about redox because I'm a little behind on the lecture. So for the next few minutes, I'm going to breeze through some more solubility stuff. Okay, and at a much quicker pace than I normally would. We've already talked about a fair bit of it. So let's take a quick look at metal oxides. So we've talked about the metal complexation. Talked about how the hydroxides tend to be able to precipitate, and we developed these equations saying, okay, we've got this beta, this cumulative constant that we can derive, and ultimately we can get some equations where we're relating the solubility of, let's say, FeOH2 to H+. So we can get some sort of pH diagram. And don't even worry too much about this slide. I'm just saying we've got these multiple spots. Given that, we might like to figure out how much total iron or how much Fe2+ perhaps is in solution, and at what pH is it going to start precipitating? Like, when do we start getting this stuff to come out of solution? Do we need to design our system so that we don't dissolve it or that we do dissolve it? What do we need to do? So that's often a question we'll ask. So using all those complicated equilibrium equations that we can derive, we can then go and figure that out and plot that. So with all of that, we could get a big table, things like this. And all I really want to show is with different pHs, here's all these different iron species, and you can actually take a look. You can even make a plot of the ion activity product or a column with it, calculate that for each of these, and at some point we figure out that the ion activity product is greater than our solubility product. And we say, these cases, and the table from the book highlights right here and right here, those particular pHs, 9 through 11, we have this ion activity product that is greater than the solubility product. So under those cases, we know, all right, we have solid formation. On a graph, that would look like this, where we have each of those equations that we talked about. Maybe we could just say, like, here's equation number 1 and 2 and 3 and so on. And each provide us some plot given the pH. It will have some function that looks like that. And then we plot it all out, and then we figure out, okay, everything above this curve that was created here should be precipitation. So of course there's some, at any pH you have precipitation above some concentration of iron, but here's where it dips, right? So we have the solid iron forming, and if we really wanted to get the most precipitation with the least amount of iron, let's say if we're doing some coagulation and flocculation, then we would target that dip and say, can we get a condition near there to promote the precipitation? That would be the way to get the most iron out of solution. Okay, so some things like that. What I mostly wanted to show you is that each of these equations, when we have, let's say, that Fe2+ is equal to this K star times H plus squared, right? That's going to be tracking one particular line, and we can plot that line. That's how we could develop a plot like this. So here we have another one. Not going to dig into the derivations of any of these, just noticing that we can sometimes have a square value for H plus. Sometimes we can then take the log of that, and that becomes a 2 times pH. So in this case, 2 times log of H plus, that's saying minus 2 pH, right? So that's why we have a slope here of minus 2. Okay, so we've actually looked at this type of stuff a little bit before, just highlighting that we can make a complicated graph out of it if we do all this stuff, putting all these things together. That's the point, and that's also what the Mintech software can do, right, is to assemble these types of graphs. So a lot of times we will go and obtain this type of data, obtain this kind of graph, either from a lookup table or from a computer system to do that. But from everything we've learned so far, you could also do it. All right, we haven't really practiced and honed in on, okay, let's do that for this system so we know that we can do it. But you can do it. That's based on what you've learned. That's the point. Okay, I want to give a couple quick overviews of common solubility cases we see in the environment and in environmental engineering. So here's a couple. One would be phosphates tend to be rather insoluble. So most +1 charged stuff tend to be pretty soluble. 2 plus and 3 pluses, or minuses for that matter, tend to have lower solubility. So when we get phosphate, and it could have a 3 minus if under basic conditions, if we do the PO4 3 minus, it will tend to precipitate with a lot of stuff. So in nature, we typically only find about 1 milligram per liter or less as free dissolved phosphate and in different forms. So, and in fact, biological systems are pretty sensitive to that, and you can get eutrophication, too much algae growing and stuff, if you add in some extra phosphorus, because it's like, oh, there's something here I can use. Let me consume that. That was my limiting nutrient. We're going to grow a whole bunch. Okay, so hydroxyapatite is one common phosphorus mineral, and we see here the molecular formula is actually 5 calciums, 3 phosphates, and 1 hydroxide. So that's, in this scenario, when we think about that solubility ratio correction, we suddenly have lots of molecules that are forming the one deal here. So 5 calciums, 3 phosphates, and a hydroxide. So that's, you know, a case where it becomes more important. Okay, if we wanted to plot that or take a look at how solubility of this hydroxyapatite appears, we can plot it versus pH. We'll see that we get above this line here, we get solid. So we get the solid precipitation. So at highly acidic conditions down here, we're not precipitating anything. So it's still stuck in solution or in the dissolved phase. If we go over to more of a neutral pH, we're kind of in between. And we can even take a look at about what concentration are these species at. And as we get more and more basic, in this scenario, we get quite a lot of precipitation. Another phosphate mineral would be fluoroapatite. This is essentially I think this is part of tooth enamel that we might want fluoride in our toothpaste, for example. There's some question about, do we really need it in our water if you could just have it in your toothpaste? So you probably heard some news about that ongoing. There is clearly a dental benefit for having your teeth exposed to fluoride so that fluoroapatite can form, kind of provides a bit of a extra passivating layer, you'll say, at the surface of your teeth that makes it more resistant to damage from damage in general, but also from attack from kind of chemical damage, because it remains pretty insoluble as a good barrier. So that much we do know. Okay, another notable thing we deal with a lot with wastewater, in fact, is struvite. So this, if we take a look at the mineral composition here, we've got magnesium, we've got ammonia, we've got phosphate, and water. So the fact that we have ammonia and phosphate, which are both pretty common in wastewater processes, a lot of these biological degradation products. Magnesium is not uncommon either, so that's around pretty often. If the pH is in the correct situation and you have plenty of these molecules, you'll get lots of struvite precipitation. It can cause a lot of fouling or problems with the plumbing because it's just going to be precipitating and narrowing our pipes over time, right? No fun. Now, in a water distribution system, we don't have nearly so much ammonia, probably no ammonia in water distribution. So we don't have struvite forming, but we do actually have some mineral deposits in a typical like drinking water distribution system, and we actually want that. We'd much rather our pipes eventually close up and not work anymore compared to going the other way, because it's all equilibrium, right? It's typically going to go one way or the other. We never want our pipes to be eroding away. We always want something to be adding to them instead of subtracting from them. So over the course of decades, we want them to eventually start looking like that. I mean, it'd be great if they didn't, but we want that instead of them eroding and breaking, because then we get contamination coming in, we get all sorts of problems. Okay, so struvite can be a big problem, but if we also look at it, perhaps we can actually promote it in a controlled manner and then capture something that would be really good for fertilizer. So adding magnesium to wastewater, causing that precipitation. I'm not sure if that is done. I think it perhaps is, but that's the type of thing we can design or think about when we are trying to deal with some unwanted precipitation like this. And fertilizers generally are going to have some mixture of nitrogen, especially ammonia is a good form of it, and phosphate. Sometimes you'll have some other stuff in it, but those are typically the limiting ones. So if you could just pull that straight out of wastewater by adding a bit of magnesium, could be a good way to go. Okay, another notable one, and we're going to touch on this as the last topic of our course, so not go too far right now, is carbonates. And carbonates, carbonic acid dissolves into water, CO2 dissolves basically to form carbonic acid. And then we have a lot of minerals that can form with carbonate. So calcium carbonate, magnesium carbonate, and then many other mixtures. So we've got and sometimes just forms, like what is the crystal structure. So we've got calcite, argonite, vaterite, lots of stuff like that. A lot of the ocean is super saturated with respect to calcite in the upper areas. So the diatoms and things that make their shells out of it are very happy to promote that condition to start a precipitation reaction and then have a shell. Right? It's almost like you want a house, and so you you draw a circle in the sand, and suddenly the house grows around you, right? Diatoms are pretty cool that way. Okay, so we talked about the more complicated diagrams. They can be a little simpler, and so we'll probably come back and take a look at these when we cover the carbonate system in a little more detail. But just to show you real quick a bit of a preview and to connect that same concept, we can have different equations mapping out different sectors of a diagram to figure out under what conditions do we have solubility. So again, we've got a couple pH graphs here with calcium on the y-axis, and at certain pH ranges, one particular equation will dictate, okay, here's the slope, and then maybe at a different pH range that we have a different one, and then finally a third one. That's for this, what we'd call a closed system. So we do not have air exchange with the atmosphere. But when we do have air exchange with the atmosphere, that changes things, because CO2 is kind of a special animal. it dissolves as this carbonate, but it can also degas off as CO2. So depending on where the pH is, that will actually tell us how much of the carbonate we have. So carbonate is here as a function of pH, and therefore, and not just carbonate, the total carbonate is, therefore the pH graph ends up just looking like this. And so we'd have solubility under those conditions. And again, the equations are just going to come from our equilibrium equations, not going into depth with that right now, just showing you we can have equations as a function of pH to plot out where are we at equilibrium. If we're on the above that, then we're supersaturated and we'll have precipitation. And if we're below that, we're not saturated and we will not have solids in the system. Okay, make sense? All right, final thoughts on precipitation. There's a couple things I didn't really talk about. We did talk about saturation ratio. Didn't really talk about the nucleation process. So if you've ever done that crystal growth experiment with the supersaturation of sugar, you'll recognize once you dip something in and promote, you have a seed for the crystals to start growing on. That's important. So if we really wanted to go into depth into maybe mathematically modeling how fast that lead iodide was precipitating in that video, right? It started looking like a little gold snowflakes, kind of. If we wanted to map that out or understand the pace that would take, which could be very important for some processes, well, we can look at the kinetics of it, and that'll depend on how big the particles are, and several other factors, temperature, all sorts of things, plus the saturation ratio, which now we've talked about. Okay, so just wanted to make a couple notes. If you dive into the world of precipitation and particles and nucleation, stuff like that, you'll find that the speed there and the particle size, all of that is relevant. Okay, so I want to shift to redox chemistry. And I have new slides for that, so we will go on to that shortly. So overall, what is redox? Redox is the shorthand version of saying oxidation and reduction reactions. It just sounds better. Oxred just doesn't sound great, so redox is a little easier to say. So reduction and oxidation reactions, or chemistry. So to oxidize something is to take away its electrons. The most common tangible practical thing you might think of for oxidation is, well, there's a couple things that come to mind. One would be if you have a fire and it's burning, you are oxidizing something and the oxygen in the atmosphere is grabbing electrons away from whatever fuel is burning. Is essentially what's going to be happening. And that's releasing energy because the bonds are breaking and all that. So an oxidizer is something that wants to take electrons. They're greedy for electrons. So oxygen, O2, when we have atoms, we'll talk about this, or molecules in a state like this with no charge, it's just that atom, we have a net zero charge here, right? And so the oxidation state for these for each of these is 0, but we often see in molecules that the oxygen likes to act like it's a -2. It would kind of like to have 2 extra electrons. So it would be very happy to then go to water, where we have kind of a plus and a plus and a 2-, sharing together. And this is, we'll come and more formally talk about this in a minute, but we now just changed the oxidation state of oxygen from a 0 to a -2. So it stole 2 electrons away. So every time we have one molecule of oxygen, it is stealing 2 electrons from whatever fuel, and now it has 2 extras. And yes, that would be, another way to say that is oxygen itself was reduced. So oxidation is when you're stealing, or they have been stolen from you, you've been oxidized. You could also force electrons on something and say you've reduced that something. So that's the oxidation and reduction. Another common way we will see oxidation, or you'll have seen it in your life, is if you've seen some metal rust. That is an oxidation reaction where we went from, a lot of times it's iron, because that's the typical one we see, and we saw that it went from kind of a shiny metal, and now it's kind of an orangish, reddish powder. The iron has been oxidized into a, let's say, from Fe0 to Fe2 plus or even 3 plus. So that means the iron has been oxidized, perhaps by oxygen doing the oxidation. Okay? All right, so reducing agents, just the flip side, they tend to donate, or a reducing agent would be this thing that gives electrons away, and something that was reduced had gained those electrons. Okay, so it's easy to say this backwards and easy to not quite say it perfectly, but the real confusion is it the thing that's doing the oxidation, or is it the thing that has been oxidized? That tends to be the tricky part, right? So just remember, oxidizing is taking away electrons from something, and reducing is kind of forcing electrons on something. So oxidation, the other way to say all this here at the bottom, oxidation is the loss of electrons by that species. So iron was oxidized because it lost electrons, and reduction would be the gain of electrons. So oxygen was reduced because it gained electrons, but it was the thing doing the oxidizing. Okay, so try to keep that in mind. Come back here. I have it written properly, so if I said it wrong, you can come back here and look at that, or look at the internet. Make sure you get that right, because that'll be very helpful. It's very fundamental. Just knowing which one we're talking about, okay? All right, so again, I'm going to recommend this YouTube page. It's a fun one. He actually has two. One is explosions and fire. So there's a lot of redox involved with explosions and with fire. And then if you just like chemistry in general, he has another one called extractions and ire. And if you've ever done any chemistry, chemical extractions might make you irate. So that's why it's the pun there. So I'll try to at least get one of the videos here for you in a bit. In fact, that is a good one. Maybe it's too long, half hour. Yeah, might be more fun to listen to him instead of me. Fluorine is an extremely potent oxidizer. So you get some really crazy, weird chemistry if you're using that instead of oxygen. But I have a few more slides, so we're going to pick back up into a few more slides before we get something more fun like a video. That'll probably have to wait for next time. Okay, so we've talked about what is redox. So I mentioned this already, but we're going to be a little more explicit now. So the oxidation state of a given atom is essentially how many electrons does it have extra, or is it missing, compared to a zero state. A lot of times we will call it zero valent whatever, zero valent iron, the Fe0 there, referring to the condition where the valence electrons are full and nothing else interesting is happening. So when we have O2, which is molecular oxygen, or ozone, which is O3, hydrogen gas, H2, helium, nitrogen gas, we can even have things like fullerenes, which you probably never heard of. That's little carbon soccer balls. Iron, diamond. Anytime we have just one element, and that's it, we're going to have it at a zero valence state. So that's kind of what we're referring to when we have oxidation state of 0. So then if we take a look at Fe2, this is ferrous iron, you'll often see it with like the 2 Roman numerals written like that. That's referring to the fact that it's in the +2 state. That means if it's +2, the charge is +2, that means it's missing 2 electrons. Now, iron tends to be fairly happy that way. It can be in the 0 valent, or it can be in the 2+ or the 3+ state. So, given that, that's the way we write this is that its oxidation state is 2+, because it's missing 2 electrons. So, a lot of the simple ones are very easy. We've been talking about it throughout the semester. Sodium, for example, is a 1+, and all the halides are going to be a 1- in their typical ionic state. Of course, we can put it, like we can have Cl2 gas, right? So Cl2 would be a gas, and that's in a 0 valent state, right? So in that situation, we could have it in the 0 state, or when it's dissolved as an ion, a lot of times it's in the 1- state. Okay, so we kind of know that. We've seen a lot of that. The more complicated ones tend to appear when we have some what we might call polyatomic ions. And we now have, let's say, phosphate or HSO4- or nitrate or nitrite. So we have a few rules to help us with them. And this gets even more complicated and a little bit random feeling when we get to transition metals, because they have several oxidation states. They've got lots of molecular orbitals. But for the moment, let's take a look at the more common ones where perhaps we can piece together some of the rules that govern things like these ones that we've seen pretty commonly, right? Phosphate. How do we know what is the oxidation state for the P, for example, or for the oxygens? Do we have any rules to do that? Well, it turns out that we do have a few rules. First of all, we can decide which ones to assign electrons to. We would start with the most greedy atoms. And by greedy, I mean electronegative. Right? We talked about that before. Fluoride is essentially our most electronegative atom. So we're going to give electrons to that one first. And so if we have some molecule that did have a fluoride in it, we would go ahead and say fluoride's going to be happy first and give it as many electrons as it needs. Then oxygen, then chloride, then sulfur, and later we can say nitrogen would be given the electrons before carbon, carbon before hydrogen, and then we would treat all the metals as electropositive. So they're going to get last pick, and they're the ones that are going to be lacking the electrons typically. This also means that fluoride would take oxygens from electrons, from chloride, for example, if we had those two doing some sort of interaction. Okay, there are a few elements that really only exist in one oxidation state outside of the elemental, but a lot of them have multiple. So things like carbon, nitrogen, sulfur, chlorine, they all have at least 2 oxidation states where they can be found. Some things, I don't think sodium goes anywhere different. I think it's just +1. So there are some that are just very simple, but a few of these have several. So here are a few rules that we can follow when we're trying to sort out, okay, answer that question of what are the oxidation states for sulfate, right? What is the sulfur? What are the oxygens? So the rules that we can follow here, first would be for monoatomic substances, it's equal to the charge. That's a fancy way for saying duh. Okay. Sodium, okay, it's a +1, right? Al3+, what is it?
3+.
Yeah, there we go. Okay, So that we could write that as a 3, right? Okay, so that one's obvious. Number 2, except for metal hydrides, which are not common in environmental systems, hydrogen bound in compounds is assumed to have an oxidation state of 1+. So there's a few exceptions, but we're going to ignore those metal hydrides. Pretty much we treat hydrogen as a +1. Okay? So when we see it in water, or we see it in, let's say, sulfuric acid, H2SO4, the hydrogens are going to be +1. Oxygen is pretty much -2 in almost all situations. So we can say that it's going to be -2 unless we call it something special. So peroxides are oxygen groups that contain a different amount. So there's some examples. So hydrogen peroxide would be where we have the oxygen is containing a state of -1. So H2O2 is hydrogen peroxide. And the fact that it's named that way as a peroxide is what tells us that this is an oxidation, this is an oxygen in which its state is a -1 instead of what it normally is as a -2. So, whereas water has a plus for the hydrogens and a 2- for the oxygen, hydrogen peroxide now has plus for the hydrogens and a minus and a minus for the oxygen, making it neutral, right? So if you ever see now anything that says peroxy or peroxide or whatever, you can recognize, this is referring to a scenario where the oxygen is in a -1 state. All right. A couple more, or 3 more really. So, we also have, so in covalent compounds, the oxidation state of each atom is the charge remaining when each shared pair of electrons is assigned completely to the electronegative of the two forming a bond. If an electron pair is shared by atoms of the same electron neutrality, like a carbon-carbon bond, it's basically split between. So if we have something shared, it's going to share towards the electronegative, the electrons will, and it will all fill in accordingly. Sometimes we could share them split right down the middle if they're the same atom. Yeah, and there is a good little note here. I'll go ahead and talk about it. So there's another one called superoxide. So if you get into any photochemistry or any radical chemistry, you might see superoxide radical anion. Superoxide if we take a look at this guy, this has been forced to take an extra electron. It's a radical. And let's see, the superoxide is essentially each oxygen has 1/2, but then this one was also forced to have an extra. I think that's the way to think about it. Anyway, it's just a little side note. You might see that in addition to the peroxide, there's superoxide occasionally. KO2 being another example. Okay. So back to number 5 here. So the sum of the oxidation states in the atoms in a multiatomic substance is 0 for the molecules and equal to the formal charge of the ions. Okay, kind of obvious again. Just if the charge is 0, we're summing to 0. Okay, and last, when multiple atoms of the same kind occur in a species, in organic compounds, this happens a lot. The element may have some average oxidation state that's really some fractional value, and we say, okay, this is kind of shared type of thing. All right, so I've got a table here. It's a little small, and I don't want to focus too much on it at the moment, but it would probably be good to take a look here to consider some of these substances. So I think, let me check real quick. Yeah, I want to spend a moment to think about a few of these atoms or these molecules to chart out, do we know what oxidation state it is? So I'm going to highlight a couple of these here. We'll start with the top. So you could probably do this as a good exercise for yourself, is to pull up these slides and block off the oxidation state, or just write it separately, and then use this as a checker to say, oh, was I able to identify the correct oxidation states for these pieces, right? Am I getting this? Am I able to get the pieces together here correctly? So let's start with ammonia, NH4+. Without looking up here, what's the oxidation state of the nitrogen? Okay, -3. Everybody agree? Okay, and so the way we can get there, right, is to treat each of the H pluses as a +1, and we have 4 of them, so this gives us a +4, and then in order to get to a net +1 for the entire molecule, nitrogen has to be -3, right? Okay, so wanted to just double check that you can kind of take a look there. We could take a bunch of these. So let's take one that's not on there, so you, just in case. Take for a moment, and before anybody answers out loud, tell me what the phosphorus is. Or I just said tell you. Write it down. Just figure out what the phosphorus is, the P, what oxidation state is that, and write an answer down, and then we'll talk about it. I have the most enthusiastic participant online. This has never happened. So really interested in giving the answer, and actually probably giving a lot of good info here. And I don't have time to connect with all of it.
Are they in this class?
No, I don't think so. We have one viewer right now, and I really don't think it's somebody in this class.
What? You just kind of stumped the pod?
Yeah, it's open to anybody. So, hi, Poojan.
Poojan.
So that's the name there. I don't know. The P. Yeah. Okay. You got an answer here?
Yes.
Okay. Yeah, and what is it?
+5.
+5. Yeah. Okay. And so hopefully what we can see is if we're treating the oxygens, so we can kind of go towards those rules that we covered. If we know that oxygen is something, we know that hydrogen is something, then we should be able to solve the rest of it, right? So even if we do put this as H3PO4, you can see how it's really, the oxidation state's not changing when we add the acid, right? Or we add the protons, we change the version of the acid. Yeah, so our guest is from India, by the way. Okay, so it's not changing the oxidation state, and we can see that we'd have +3 here, or we'll just start with the phosphate itself. Right, so we have each oxygen treated as -2 times 4 gives us a -8. So in order to get back up to the -3, this has to be +5. And our guest got the answer way before you guys did, by the way. He was ready. Okay. Yeah, he probably teaches this stuff, and he's like, "Come on, man, get it right." So don't forget the superoxide. Oh, he's enjoying it. I don't know.
How many subscribers do you have?
He says he's in class. He's in a different class, maybe. I don't know. I think it's mostly former students that have subscribed at some point and are there. So probably like 100. I don't know. I haven't ever tried to grow this as like anything more than just hosting lectures. There's been a couple times where I put like a class demonstration or something, and maybe that would be like, hey, if some other teachers see this, that's helpful. But mostly it's just for you guys, like, and anybody that happens to decide to join. Oh, he's in grade 11. I see. Gotcha.
Grade 11?
Nice. Doing some good chemistry.
So he just stumbled upon this.
I mean, he could be lying. Who knows? I'm not saying that he is, but.
Dude, him just listening to the class talking about him, like in the background.
Well, he probably can't hear you very well through the microphone. Maybe hear that you're laughing or hear something, but he's not lying. He says he's not lying. Okay, awesome, fantastic, love it. Okay, so I love it. Never a problem to have more people here. If you guys ever participating online, I encourage you to chat, because I will see it. By the way, in case you didn't know that. But yeah, all right. So can't always get to all the questions or comments, but do what I can. So now that we know something about the oxidation states, that they can be changed, we can cause some oxidation, we can cause some reduction. What we want to be able to do is balance the reactions, and we're going to do that by halves. This is what we say is we're going to do half reactions. And that will let us set up our chemistry such that we can understand how many electrons are changing, so we can track the different pieces here. So we need to, and redox reactions, truly, they have many different applications. We could look at, how does a photovoltaic cell work? How are we generating electricity from solar cells or from an electrochemical cell, a battery? How does that interact with all sorts of different things? So this approach is what lets us get the information we need for that type of system. Lots of biological systems as well. We are, photosynthesis or even just respiration are all going to be redox reactions occurring within them. So to balance it, we need two half reactions. So we'll have the oxidation side and the reduction side, and we will essentially track what happens with not just like left hand or the right hand, but it's a piece on the left hand with the corresponding piece on the right hand. So if we had, I guess the notes show it, right? If we have reductant number 1 reacting with oxidant number 2, and forming an oxidant number 1, and reductant number 2, what we look at is the fact that the 1 and the 1 match, right? So earlier we talked about zero-valent iron oxidizing to Fe2+, for example. And reductant, I probably am saying this backwards, so let me do this. No, oxidant. No, that would be, I had it right. Because the iron will be donating electrons to something, right? So if we looked at it this way, what we're going to match is the change in the iron. So the half reactions are going to extract the similar pieces, okay? Whereas the oxidant here, maybe we go from oxygen to a couple of waters, something like that. And we can see the oxidation state from molecular oxygen is 0, and in water it is what? -2, yeah. So we can see that water here was reduced, or oxygen was reduced to water, and the iron was oxidized to Fe2+. Okay, and our guest can hear you at least a little bit. So good. All right. So this is the goal, and we're going to track this we also need to add electrons if we're going to split them in half like this when charges change, we need to add electrons in order to satisfy the charge balance. So we're going to keep charge balance, and in the net, we will have electrons cancel on the right hand and the left hand. When we balance each half reaction, then we can add them both back together, and the electrons will look like they go away because we added 8 to this side and we removed 8 from this side, kind of thing. That's happening because the electron transfer happens rather quickly, and it happens molecule to molecule. They don't really transfer out into solution as free-floating things very much. That's not really a practical thing to look at. Okay, so we have a 12-step program for balancing our reactions, or for solving your chemistry addict problems or something. I don't know. 8 steps really. So first, we want to identify the reactants and products for each half reaction. So what I just talked about is is this first step, right? Is it oxygen to water? Is it iron to 0 valent 2+? What are the half reactions that we need to identify? And for each, we want to write the general practice is to put the oxidized form of the principal reactant on the left and the reduced on the right. Now this is not incredibly important because you can always flip them if you do it right. And it'll be obvious if you don't do it right, the electrons won't add up to 0. So if you do it wrong, you'll have like plus 20 electrons and you're gonna be like, I think I need to switch something. So with a little bit of practical, logical double checking, you should be able to find that and figure that out. So step number 2 is balance each half reaction. So we just have one of the half reactions. We're going to take them one at a time. We balance it for the atoms other than hydrogen and oxygen. So we're going to save hydrogen and oxygen because those are going to be slightly fancier. Again, this is going to be, in this case of aqueous chemistry, we've always got some hydrogen around and some water at least, right? We know we have water and hydrogen. Oxygen, yeah. So if we had, let's say, iron, we need to make sure that we have the same number of atoms on each side of our equation, obviously. Next up, for number 4 here, we would balance the hydrogens, number 3, I'm on number 3. Balance the oxygens in each half by adding enough water. So the water will take the place for whatever we need to do if we needed more oxygens. For example, you saw me earlier talk about using oxygen to oxidize something, and I just said, well, how about we add some water? That's essentially what we're doing there, right? So at that point, number 4, we balance the hydrogens by adding enough H+. So in this case, if this is my half reaction up here, I'm out of balance in terms of H+, so I need to add 2 hydrogens, 4, right? And note that we're not adding this as hydrogen gas, H2. We're going to add it as protons, H+. It's not too common to get hydrogen gas in your water, and it can cause some problems if you do. Okay. Number 5 would then be balancing the charge by adding enough electrons to match, well, to satisfy the charge. And what we should see is this, the number of electrons should match the change in oxidation state that we saw. Okay, so in this little example that I've been kind of working on up top, it's really the half reaction of oxygen as an oxidizer, reducing oxygen, we need how many electrons? And on which side? 5?
Should be 4.
4? On which side?
4 on the left side.
4 on the left side. That make sense? Yeah, we're just balancing the charge here, right? So I'm going to add 4 electrons here so that it counteracts the 4 plus right here. Okay. Okay, so might have been overcomplicating it there for yourselves, but we're just adding enough of it so that it balances out, and we're good. So now, part 6 here, we're going to double check the balance for each side and each half reaction, make sure everything's good. And by the way, we can stop and double check. When I said it should match the oxidation state, the change in oxidation state, we know that oxygen was going from 0 to a 2 minus, right? Oxidation state. So we added 4 electrons. It then makes sense when we realize we added 2 waters. Right, so because we have 2 waters, the total oxidation state was 4, because 2 times 2, right? So that means 4 electrons, that fits, it's looking good. We probably balanced that correctly. So at this point, number 7, if we're adding 2 reactions, sometimes we might have to account. Let's say we have 1 reaction, we have 4 electrons here, but the other half reaction has 8 electrons. We'd have to multiply 1 by 2 so that the net electrons match, and you'll notice all the rest of the balance will end up matching too. So we just make sure the electrons go away all the way, basically, when we recombine. Okay. Finally, we're going to subtract the reduction half from the oxidation half reaction. We could also flip it if we need to. Flip one reaction so that it's going from reduced to oxidation and add them together. So basically we're just going to combine them in a way that gets rid of all the electrons. Okay? It's not really worth thinking too hard about where they are, so long as you're ready to make sure that it's making logical sense in terms of the electrons go away. Okay, I have a couple examples here, although Pujan is providing a few more examples, so maybe I'll write one of those if you want an additional one. All class, he's like, oh yeah, do this one, try this one. So you can probably go see it. Probably good homework review, by the way. So just go back and watch this and see these comments. They should be recorded. So some added content for you. So we have just a few minutes left in class, but let's do at least this first one. Manganese, we're going to convert manganese to manganese oxide by chlorine gas, Cl2. So see if you can tackle that. Take a couple minutes. Remember, we're going to start with splitting it in half and then working to balance and understand which each half is going to. I'll give a couple hints here. Chlorine as should be 0 valent. This should be going to chloride pretty much, right? So that should be part of what's going on. Of course, I didn't balance that here for you yet, but typically when chlorine is going to react with something, chloride will be the reduced state of it. All right, so you've had a little time to think about it. So I'm going to walk you through these. I think we could probably finish. Okay, so first, let's take the manganese. Mn2 plus is the more oxidized form of the two, so I'm going to put that one on the left side. Then, actually, it's probably not. It's fine. Just realized. If we look at MnO2, that should be in a 4 plus state, right? So I totally started that backwards. So it probably helped to consider for a moment what states we're in, because this should be +4 if each oxygen is -2. So we'll start there. I'm going to leave myself room in both cases to add some extra stuff on the left, for each equation. Now, to balance the two oxygens, we need to, first of all, the manganese are balanced. We got one on each side. Then to balance the oxygens, we need 2 waters on the right here. Of course, now to balance the hydrogens, we need 4 hydrogens over here. Okay, about the charge balance, we need electrons somewhere. And what I didn't really mention is we don't really need to get to 0. We just need to get the sides to be equal to each other. Okay, because if you could go to 0, add 4 electrons on the left, but you need 2 electrons on the right. And what you'll find is that just counteracts each other. So you'll have a net 2 electrons on the left. Either way, you're getting kind of the net charge to the same spot. Okay, so that should be the manganese side of it for that half reaction. And I guess I didn't need quite so much space, so I'm just going to move this up here. So when we look at chlorine, chloride, we're going to put the higher number on the left. It's probably the better way to look at it. So Cl2, did that backwards also. This is going to be a bit of a simpler system. This is going to give us 2 chloride ions like that. There's no oxygens or hydrogens, so all we really need to do is balance the charge. So with this, we need to add 2 electrons, right? Okay. So at this point, all we have to do is combine these in a way that the electrons are going to go away, right? So in my mind, I'm thinking to myself, okay, I'm just going to rewrite this to say 2Cl minus. Well, another thing we probably should keep in mind is when we know something is the oxidant, we are oxidizing manganese by using chlorine. We should put that chlorine that's the active thing on the left, because that is a reactant for sure. So I'm going to keep this chlorine, Cl2, on the left and rewrite the other one in order to make it make sense, to have the Cl2 plus 2 electrons plus this stuff, because I have to flip that one, plus manganese 2 plus, and a couple waters will be, by the way, these are technically equilibrium reactions as well. So then we'll have on the right side, we'll end up with 2 chlorides, and then all of this stuff over here. So I'm going to write that out, balance it, and we'll get out of here. So plus MnO2 plus 4H plus 2 electrons. You'll see the electrons should cancel, and what we're left with should be balanced. So that would be our balanced redox reaction. So we'll pick up there next time and carry on. Have a happy Easter.